Hi guys, Mr. Sonnenberg here. So we're working with Science 9, Matter and Chemical Change. This would be topic 3 in your textbook, and today we're going to talk about what are elements. So where do they come from? Who discovered them? What are they? So early on in the early days, the first recorded or recording of what we thought were elements it came from the ancient Greeks, and they actually thought that elements were in four components, and that was earth, air, water, and fire. And so basically, what they said was that these four elements were always in combination, and they had varying hotness, coldness, dryness, and or wetness. And so they thought that they really combine in different ways, but they were all the basis of life. And so they called these four, the earth, air, water, and fire, the elements. And that's kind of where the elements originated from. So when we're taking apart matter, this is something scientists started to do. They started to take this matter apart and they started to break it down, and they just wanted to keep breaking it down and determine whether it was a pure substance or a mixture. So how did they do that? Well, they did things like heating, burning, mixing, and cooling. And they just kept breaking down this matter, and they wanted to see how far they could break it down. So there was a man by the name of Antoine Lavoisier, and he basically said that elements as pure substances, or elements were pure substances that you couldn't decompose them any farther. So basically, they were in their most simplistic form by means of chemical change. So these were the simplest form of a pure substance that you could find, and that actually stands up today. So he was one of the first chemists that actually used balanced view on chemical change. And so this balanced view is going to lead us into the law of conservation of mass, and that's what's known as today. So this law basically is stating that in a chemical reaction, the total mass of the reactants is always equal to the total mass of the product. So we remember reactant side and product side. Okay, some two elements or compounds, they react to produce, and let's say hydrogen gas and oxygen gas combine to produce H2O. Okay, and so we've taken two elements and we formed a compound. So it's interesting though, because this law of conservation of mass is very closely related to the atomic theory, which we'll look at later, that was derived by John Dalton. And basically what it states is that atoms are never created nor destroyed. Basically all we do is we just rearrange the atoms and the molecules, and just it's just a simple rearrangement. And that's both from product side to reactant side. So the law of conservation of mass, though, it can't be used or applied to nuclear reactions. And the reason is because in this nuclear reaction, we actually lose some of the mass, and it's actually converted into energy. So this was first suggested by Albert Einstein. So if you take a look at the picture at the top, if you remember Halloween, that's who I went, or I dressed up as, and I think I did a pretty good job. We look pretty close there. So he's a little bit better looking than me, but things that I'll have to deal with. So he stated that E equals mc squared. Now it's that famous equation that people all know. So E is basically our energy, or not basically, it is our energy. M is mass, and C squared is just a very large number. So basically what happened is he's saying that a very tiny amount of mass is equal to a really large amount of energy. So if we had an open system, the mass just seems to disappear when it's in the form of a gas. So that's that law of conservation of mass. So the mass on the reaction side must be the same as the reactant side must be the same as the product side. Now another law that we have is called the law of definite composition. Now this is talking about compounds are pure substances that contain two or more elements combined together in fixed or definite proportions. So now we're talking about compounds, but we're still talking about these pure substances. So we can state that elements are pure substances and compounds. Now what we're taking here is, if you take a look at the diagram, we have 2 hydrogens on the left side. We actually have 4 hydrogens, sorry, and 2 oxygens, but we have hydrogen gas, H2, and another hydrogen gas, so we have 2 hydrogen gases, and then we have O2 gas, and if we were to write that in a chemical formula, it would be 2H2 plus O2 react to produce 2H2O. So we can also, so if we look at this, when we look at composition, and we can also talk a little bit about proportion, and we can look at the proportions of a water molecule, and they'll always be consistent, and it's going to consist in terms of proportion of 11% hydrogen and 89% oxygen. But if we were to look at, say, something different like hydrogen peroxide, then we're going to be looking at H2O2, and now it has somewhat of a different proportion, and it's going to have 6% hydrogen and 94% oxygen, but we can still break it up. But the main thing we want to know with the law of definite composition is that compounds are pure substances of 2 or more elements combined. Okay, so we're combining to form compounds, but they must still have similar or definite proportions. So we can't create nor destroy, we can only rearrange. So some new discoveries that we found. This man, Alessandro Volta, okay, he made basically what we'd say is the first practical battery, so what we know as batteries today, and he called it the voltaic pile. So what he did was he piled up a bunch of zinc and copper plates on top of each other, and then he would separate them with electrolyte soaked paper discs, and he would hook this up to an electricity source through water. And basically what he discovered was that you could take this electricity source through water, and you could actually separate the water molecules into hydrogen and oxygen gases. And so you would notice that the water level would actually go down because it was converting into a gas. So what they would do is they would take a test tube and they would actually trap the gas and then put a stopper in. And so now they could do a test. And remember those tests that we do where if it's oxygen or if it's hydrogen, we can actually do a test there where we can, if we use a glowing splint, we can actually put it near the trapped gas or the unknown gas, and if it pops, we know it's hydrogen, and if it ignites, we know it's oxygen. So this process was called excuse me, this process was called electrolysis. So this is what they use to split molecules into the elements. So scientists nowadays, they still use electrolysis, but they've found ways that they can isolate the elements potassium, sodium, magnesium, calcium, strontium, and barium. So if we take a look at the diagram, we can see that if we have water and we hook up to our voltaic pile or our battery source, okay, so it's going to produce the electricity. What we're going to do is we're going to see some bubbling occurring, and bubbling is basically now what we're doing is we're separating a gas. And so if you look at the diagram, you can see that the O2 gas is trapped and the H2 gas is trapped. And so now we're separating compounds and breaking them down any farther. So basically what that helps us to see is that elements cannot be broken down or simplified any farther, but compounds can be broken down into their elements. So I talked a little bit about Dalton's atomic theory. Well, basically he had 4 points. He said that all matter is made of tiny particles called atoms. Then he also said that atoms cannot be created, destroyed, or divided into smaller particles. So basically saying that, we just rearrange. Then the third point was that all atoms of the same element are identical in mass and size. Um, Atoms of one element are different in mass and size for the atoms of the other elements. So if I was to take the, let's just say oxygen and hydrogen, well, they're going to have different mass, different size, but if I was looking at numerous oxygen atoms, they're all going to be the same mass, same size. Then his fourth point was that compounds are created when atoms of different elements, they basically link together in definite proportions. So he's kind of said they hook together. So I just have a couple definitions here. So the first one are elements, and I'll just write that in, elements. And so those are pure substances made up of only one type of particle or atom. So each element on the periodic table has basically its own unique set of properties, and we can't simplify it any farther, like we said. And then the second is compounds, and I'll just write that in there, compounds. And those are pure substances made up of two or more elements chemically combined together. So they chemically combined, and then we can actually break them down into the elements. So, and this was created by this man right here, John Dalton. So we have these laws, theories, and models and observations. But what are laws? Well, really, they don't explain anything. They just describe and summarize what's been happening. But then we look at theories. And basically a theory is just an imaginative way for us to explain why something's occurring. Okay, and then there have been several models, and we're actually, the next screencast is going to talk about some of the models, the atomic models over history, which is something I really enjoy. But basically, so what we look at in these observations is we need observations, and then we form hypotheses from there, or our hypotheses from there. So, and basically, we need to do this as many times as we can, and form these experiments. And then from these experiments, we are going to either develop theories, or we're going to revise our hypothesis, and we continue doing that as many times as we need. But after that theory, there's usually a lot of time and much more experimenting that occurs, and we have a revised theory that occurs. And so the next screencast we're going to look at is basically a brief history of the atomic theory, and we're going to go through, we're going to talk about we're going to talk about John Dalton again, we'll talk about Rutherford, Bohr, and then kind of the quantum model that we see today. So I hope this screencast has helped you out, and that's all we have for now.